Okay, so let's continue with another example of an explicit surface in 3 dimensions. So we'll take a surface and it will be described in probably the most elementary fashion you can imagine. We'll just write its position as a point on the xy plane and then a height above it. So r of x and y will be our mesh. Will it be equal to x, y, and the height, h of x and y. So h of x and y is the height above or below the xy plane. Okay, h of xy is the z coordinate of s. And I've drawn it here for a particular situation where the surface all lies on one side of the plane xy. The objective of this exercise is actually to get an interpretation of the second fundamental form. We'll want to see that the second fundamental form registers or measures the distance of the surface off of a tangent plane. Okay, and so I'll be choosing the xy plane to be the most convenient of all. Okay, and we'll manipulate it in just a moment. But at the moment, let's just imagine that I have a given xy plane as shown here. Okay, and a point P and then a height up here, and I have a surface as drawn here in the red that might lie above or below, or part of it above or part of it below that xy plane. Okay, so we want to do the geometry of the surface, and we know that the geometry of the surface is all determined in terms of the tangent vectors to the surface and the gradients of those tangent vectors. So I have to compute r sub x, the derivative of r with respect to one of the parameters, and I've indicated it here. Differentiating r in the x direction, I get dx by dx, that's a 1. Okay, and then dy by dx, that's a 0. And then h derived in the x direction, I write that down there. And so similarly, I do that in the y direction, and then the rxx and the rxy and the ryy, because I know I need all of those derivatives to make my first and second fundamental forms. So to form the first fundamental form, the coefficient e is the dot product of r derived in the x direction with itself, and so that's just 1 plus h of x squared. Okay, and etc. I make the rest of it. Okay. To form the second fundamental form, okay, I know the formulas for those in terms of the gradients, and so I form them here. So little e is h derived twice in the x direction, divided by the magnitude 1 plus the square of h sub x plus the square of h sub y quantity to the 1/2 to normalize it appropriately. So here's e, little e, here's little f, and here's little g, just going back to our basic formulas, okay, for the second fundamental form in terms of the gradients of the point P on the surface. I can also form my normal, okay, so I have to take the cross product of r sub x and y sub x, and that's in the numerator, and then it's normalized, and I've written that down here. Okay. So that's the deal. Now let's try to learn something from all of that algebra. Okay. Well, what I'm going to do is just to choose to orient the xy plane so that P is at the origin. So okay. So I'll just move things around. Okay. So that P is at the origin. You know, I might imagine having a surface here. Okay, and a tangent plane here, like that. And now I'm just going to rotate things, okay, so that the tangent plane is the xy plane, and the origin is the point P. And then I'll rotate, okay, the xy plane to my convenience as well, and we'll do that in just a moment. Okay, so P will be at 0, and I'll take the xy plane to be the tangent plane itself. Okay. Okay, which means, of course, that h of 0, 0 is 0, and the gradients, h sub x and h sub y, is equal to 0, right? That puts the xy plane coincident with the tangent plane. Okay. so I do that. And then I can, for example, compute the difference of the height from the tangent plane. In other words, I'll Taylor expand h of x and y near P. So h of xy, well, that'll be the leading term, which is h of 0, 0, that's 0. Then there'll be first order differences, but I chose the xy plane to be the tangent plane, so those first order differences vanish, okay? And so I only get second order corrections plus dot, 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 higher order corrections. And the second order corrections are just written down by the formula of the Taylor expansion. Okay, well that's not so bad, but I can clean that up a little bit, right? Because I can now rotate the xy plane to my convenience. So I'll choose the x-axis to be one of the principal directions, okay, of the second fundamental form. So the x direction will be along the eigenvector of k1. And then the y direction is guaranteed to be along the curvature direction k2. Okay, so I'm orienting the xy plane so I diagonalize the Weingarten map. Okay, so one of the directions, the x direction, is going to be the eigen direction with the eigenvalue k1, the large one, and the y direction will be the other. Okay, so in this basis, then, that diagonalizes minus n prime, the Weingarten map, and the 2 by 2 matrix, the matrix representation of the Weingarten map was called little a sub ij's. It's diagonalized now. So the off-diagonal components are 0. It's just k1, k2 on the diagonal. Off-diagonal ones, elements are 0. I look back in my formula from a couple lectures ago, and I see that means that I've chosen the xy axis to rotate it so that little f is equal to 0. Okay, that makes aij diagonalized. But if little f is equal to 0, then I look back on my previous page and I see that implies that I've chosen the x and the y direction so that hxy is equal to 0. I differentiate h in the x direction and the y direction, and I get 0. Okay, so I've just chosen a very convenient orientation of the tangent plane to accommodate that. Well, that's the best I can do, because now the Taylor expansion for h of xy reduces down to just this simplest of all possible quadratic forms. Okay, so finally I want to identify h sub xx and h sub yy. Well, I look back at my formulas, okay, and I see what that means. Okay, we have a situation where the off-diagonal element in the second fundamental form is 0, and the off-diagonal element in the first fundamental form is also 0. Little f, it's capital F, is equal to 0. And we've already seen that in those situations, the principal curvatures are just the ratio of E of the second fundamental form to the E of the first fundamental form, and K2 is the ratio of little g to capital G. Okay? And so, in this particular case, E was equal to hxx, okay, and G was equal to hyy. So I can replace hxx and hyy with little e and little g. I recognize that those quantities, because capital E and capital G are 1, are just the principal curvatures. Okay, so the dust is settled. We've done our algebra, and now we have that the height of the surface above the tangent plane is just 1/2 a quadratic form, okay, and the coefficient of x squared is k1, okay, the principal curvature, plus a term that goes like y squared, and the coefficient there is the other principal curvature k2. Okay, and that's what we wanted to show. K1 is proportional to little e, so this is proportional to the second fundamental form. K2 is proportional to little g, second fundamental form. So this is just proportional to the second fundamental form. So the second fundamental form tells you how you embedded the surface into R3, and it tells you the rate at which the surface deviates from flatness from its tangent plane. And that's a general result, and a very useful and intuitively important one. So I've tabulated those things here. The second fundamental form tells us how fast the surface deviates from its tangent plane. Now I can read off a few facts. If the Gaussian curvature is greater than 0, that means K1 and K2 have the same sign, because the Gaussian curvature is the product of K1 and K2. So then the surface lies on one side of the tangent plane. It might be that K1 and K2 are both positive, and so my pictures in the previous sheets of H, X, and Y are as shown. Okay? H is above the tangent plane. However, if K is less than 0, if the Gaussian curvature is less than 0, okay, then the principal curvatures have different signs. This term has a different sign from this sign, and so you read off that some points on the surface are on one side of the tangent plane and others are on the other side. Okay? So in that case, the surface looks like a saddle. It goes down on one side and up in the perpendicular direction, like a saddle on a horse. Okay? So it's like a saddle. That's how we interpret capital K less than 0, and this is what it means then in terms of the second fundamental form. Okay, so that gives us a nice visualization of the second fundamental form, and that will help us as we move on. Okay. So now back to general features of differential geometry. I'm finished with my illustrations now, and I want to come back and think about the Gaussian map, and I want to think about the Gaussian curvature a bit more. Okay, so this construction that we're going to do right now produces a geometric interpretation of the Gaussian curvature. It's the geometric interpretation that they say Gauss originally invented. The Gauss map assigns a unit vector n hat to each point of P. Okay, so I can look at the mapping from the surface to the sphere. Okay, through n hat. The element, the area element on the unit sphere is of course just dn in the u direction cross dn in the v direction. So I might imagine beginning with a surface, and I put a UV mesh on it. Okay, I parameterize it, put a coordinate system on it, and then I have the mapping to the unit sphere. Okay, at a particular point. Okay, and I put the same mesh on the unit sphere. That's a convenient thing to do. Okay. Now on the original surface, I know how to label my unit area. I just consider r sub u du cross r sub v dv. I form the parallel pipets at any particular point along my mesh. Okay, and the cross product of those two characters gives me the area of the parallel pipet. Okay, and it gives me a unit vector, the normal vector. Okay, associated with that area, the outward vector. Okay, so therefore, when I'm on the unit sphere, r is replaced by n hat, and so my area on the unit sphere is just dn sub u cross dn sub v, and so I write it down like that. Okay, now I can relate that area to the area on the original surface. Here's the area element on the original surface, as we've said. Here's the area element on S2 on the unit sphere. I've written a prime here to indicate that it's different than the area on the original surface. And so how can I relate both of these? Well, sure. Well, I know the Weingarten map. Okay, I know that n sub u is a vector. Okay, in the tangent plane, so I can parameterize it in terms of the vectors that span the tangent plane, r sub u and r sub v. And I know that the coefficients in that expansion are nothing but the Weingarten map that we've already studied. And so I write that down here. Okay. Okay, so that's easy. So now I can calculate the A prime, the area element on the unit sphere, the Gaussian map, and I do that here. Okay, and then I do my cross products, easy as pie. Okay, and I accumulate the A's. And I see that the A's accumulate to form the determinant of the 2 by 2 matrix times R sub u cross R sub v du dv. So I identify the determinant of the Weingarten map as the Gaussian curvature. And what's left behind? Well, that's just the area element on my original surface. Okay, great. That's what we wanted. So then we learned that the curvature, the Gaussian curvature at that point, is just the ratio of those elements. And if we want to state what the Gaussian curvature is at a point, we have to take the limit of the areas when they go to 0. Okay, and so that's then the Gauss's intuitive idea behind his curvature. Okay. K is a geometric quantity, right? There's nothing left in here except ratio of areas. I've lost all of the dependence on the coordinatization is gone. Okay, so it's just the ratio of geometric objects. It's a geometric quantity. In addition, it carries a sign of the cross products of Nu cross Nv relative to the cross product Ru cross Rv on the original surface, and we can see that here. Okay, so here's a situation where R is greater than 0, and here I have a little patch on the original surface. The Gaussian map maps those normals into the unit sphere, and so here for this particular case, where it's a concave surface like that, so the K is greater than 0. Clearly, both the K1 and K2 in this case have the same sign. Okay, so I'm dealing with a Gaussian curvature that's positive. I see that as I go around this little circle that encloses the area of interest, delta A, that the unit normal at 1 points this direction, unit normal 2 like this, 3 and 4. And so the Gaussian map takes those unit vectors and puts them, okay, all to the origin, and then they point onto a unit sphere. And I see that as I go around this curve in a positive direction, these unit vectors sweep around the unit sphere in the same direction. Okay? And that's what I mean by K positive. Now let's take a saddle. Okay? A surface with K less than 0. We know, we just learned, K less than 0. We have a saddle, so in one direction it curves up, in the other direction it curves down. And so I make a closed curve on that saddle, and the normals look like this. I take those normals and map them onto the unit surface. So N, which points toward me like this, goes over here. Okay, and I come to 2, it points way back in that direction, it points backwards. Okay, and then 3 points in this direction, and 4 points back toward me. Okay, so it points in this direction. So it's clear that when I go around this curve in the positive direction, okay, the Gaussian map maps onto a curve which goes in the opposite direction. Okay, so I have different orientations, and that's the meaning then of the Gaussian curvature being negative. So make some figures and some pin cushions for yourself to convince yourself that I've got that right. I know it's best to make the pictures and the pin cushion yourself so that you're really convinced that we got the orientations correct. Okay, so that's then our another interpretation of the Gaussian curvature, and we'll be studying it more because in addition to these cute geometric constructions, we're going to want to be able to calculate the Gaussian curvature for a general surface, and that's the subject of our next lecture.